Welcome to This Explainer. Today, we're taking a very measured, methodical look at Demis Hassabis' recent framework for advanced AI. We're going to explore a really crucial concept: why testing these frontier models before they're released is absolutely necessary, but ultimately insufficient on its own for governing them once they're out in the world. We'll be approaching this as a careful architectural analysis, looking closely at how AI governance actually structures itself. Here's a quick look at our roadmap. We'll start by defining the frontier AI challenge and the real value of pre-release review. From there, we'll examine the deployment gap, runtime governance, a complete 5-layer architecture, and finally, the residual limits of control. Let's dive right into part 1, the frontier AI challenge. We have to begin with our core thesis, which is the recognition that artificial intelligence capabilities are evolving at a pace that creates profound systemic risks. To really frame the problem, we can look at this pivotal concern raised by Google DeepMind CEO Demis Hassabis. You see, he accurately identifies that the fundamental danger here lies in a massive asymmetry. There's this huge gap between technological velocity on one side and the much slower speed of our regulatory and public institutions on the other. So we're not just talking about a model producing a bad output. We're looking at the broader concern of autonomous action and competitive races simply outstripping our institutional capacity to keep up. And what's crucial to understand is that these pressures function as a connected system. Market competition heavily rewards speed, while essential safety work imposes necessary but often costly delays. What that creates is a deeply entrenched collective action problem, right? Every laboratory might prefer a safer overall industry, but individually, each lab benefits from moving first. So we end up with this volatile mix of incredibly fast capability growth, the potential for irreversible diffusion. Once a model is copied or open-sourced, it's out there for good, and the very real threat of dual-use risks in critical domains like biology and cybersecurity. Moving to part 2, let's look at the value of pre-release review. To address that dangerous incentive structure we just talked about, Hassabis proposes establishing a very firm boundary before a model is ever allowed into the world. Now, this intervention is incredibly valuable because implementing a common review gate creates a collective minimum standard. It directly mitigates the structural problem of individual laboratories just blindly racing to deploy. By requiring independent testing and establishing common capability thresholds, well, we can identify known failure modes, things like obvious vulnerabilities to prompt injection or biological data misuse, long before the system becomes broadly accessible. It essentially acts as a synchronized pause button for unsafe deployment. This brings us to part 3, the deployment gap. But here's where we run into an issue. Relying entirely on evaluating a model before it's released actually presents a fundamental category error in how we understand operational systems. This structural blind spot highlights a really key distinction. You see, a model is not a static object. Passing a test in a lab does not guarantee safe behavior when that same model is connected to a live environment. Model risk asks what the isolated base model can generate. System risk, on the other hand, asks what the entire assembled arrangement can cause out in the real world. Those are two entirely different questions. A model-centered review might approve the component while completely failing to evaluate the assembled system that's actually taking action. Just think about all the dynamic factors an AI's behavior is conditional on. A system that passes a model-level evaluation can rapidly become dangerous when it's embedded in a different operational arrangement. The exact same model acts very differently depending on its system instructions or whether it's attached to external APIs, what persistent memory it can access, its execution rights, and frankly, the business incentives of the organization deploying it. Risk isn't static. It's produced continuously as all these variables shift. Which leads naturally into part 4, runtime governance control. This is exactly why we need continuous structural oversight. A release gate decides if the system begins operating, but it's a control architecture that decides if each subsequent dangerous transition or action may occur. Basically, release governance is a point-in-time decision, whereas runtime governance is continuous. Without runtime governance, a system that successfully passes the release gate could subsequently be granted dangerous levels of authority and end up causing harm that the pre-release test never even evaluated. So to actually implement this runtime governance, we can look to a conceptual framework known as the energetic paradigm. Instead of merely trusting a model's linguistic outputs or treating intelligence as just output generation, this paradigm separates capability from authorization. It shifts governance to the continuous control of state transitions. Before a system can take an action, this perspective examines strict boundaries around authority, real-world tool access, resource budgets, and whether the proposed action is actually reversible. Now, let's pull this all together in Part 5, the 5-layer governance architecture. To build a truly credible governance structure, we have to synthesize these two approaches into a unified framework. Neither pre-release testing nor runtime control is sufficient on its own. This is the core concept that anchors our entire understanding. A release gate governs entry, and a control architecture governs behavior after entry. They operate at completely different temporal and structural levels of the AI lifecycle. A release gate without runtime control is simply too weak, and runtime control without external regulatory authority is too easy for institutions to bypass. Frontier AI systems absolutely require both. So these concepts build into our central thesis, which is a horizontal 5-layer governance architecture. This spans all the way from pre-release testing through to continuous public accountability. Layer 1 tackles capability review before release. Layer 2 examines the system-level deployment context. Layer 3 introduces that continuous runtime control over consequential actions. Layer 4 mandates continuous audit and learning after any incidents. And critically, Layer 5 enforces legal and political accountability. This comprehensive structure moves governance away from just checking surface behavior and embeds it deeply into the actual operational framework.
Finally, Part 6, the residual limits of control.
As we conclude this careful architectural analysis, we really must explicitly acknowledge the boundaries of any technical control system. Neither Hassabis's proposal nor the energetic paradigm is a guarantee of perfect safety. No control architecture is a complete solution. Any technical system remains highly vulnerable to corrupted institutions, managers creating emergency exceptions, rivalrous nation-states engaged in geopolitical competition, and just the unpredictable non-linear nature of physical environments. We have to clearly understand these explicit residual limits. We simply cannot govern variables that aren't accurately represented, and we certainly cannot retroactively control unauthorized open-source copies that have diffused beyond our governed architecture. So ultimately, technical governance can structure the operational boundaries, but it cannot derive legitimate social goals from computation alone. It can never replace the profound political, philosophical, and legal responsibility that we carry. The big question is, who remains answerable for the consequences of frontier AI? As we step further into this new age, that is undoubtedly the most critical question we must resolve. Thank you so much for joining me in this explainer.